Let's get into this video on decay equations. You may recall Nuclide notation. Alpha, beta, and gamma radiation can be represented in this form. Let's begin with alpha. Alpha particles consist of 4 nucleons, that's 2 protons and 2 neutrons, so the mass number is 4. Those 2 protons mean its charge is 2, and its atomic number is also 2. Beta particles are just electrons, so they have no nucleons, and their mass number is 0. They have a charge of -1, so their atomic number is -1. Gamma radiation is a form of electromagnetic radiation, so it has a mass number of 0 and an atomic number of 0. You need to learn these 3 from memory to be able to answer these questions in an exam. It is useful to be able to write decays as equations. Much like a chemical equation, the left side features our initial particles, the parent nucleus here. An arrow represents the decay occurring, then we write our products. These are the daughter nucleus and the form of radiation that has been emitted. It's an alpha particle in this case. An important rule of decay equations is that the number of nucleons is conserved in a decay, so the total mass numbers before and after must be equal. The initial mass number was A, so to make the final mass number A, the daughter nucleus will have a mass number of A minus 4. Similarly, charge must be conserved. This means the atomic numbers either side of the arrow must be equal. This makes Y's atomic number Z minus 2. These rules also apply to beta decay and gamma decay. Gamma has no mass or atomic number, so the element is unchanged. The nucleus just becomes less energetic. Questions on this topic in an exam will often ask you to write out the decay equation given a few pieces of information. Americium undergoes alpha decay to form neptunium, which has the chemical symbol Np. Write the decay equation for this process for 3 marks. First, let's note that this is alpha decay. The first step is to recall the alpha particle's mass and atomic numbers. These are 4 and 2. Next, write the information we already have into the decay equation. We know americium's chemical symbol, and we know neptunium and an alpha particle are the products. Remember that mass number is conserved, so americium's mass number is the sum of neptunium's mass number and the alpha particle's mass number. Some quick rearranging shows us neptunium's mass number is 237. This is 1 mark. Total atomic number is also conserved, so we do the same thing. This shows that neptunium has 93 protons, which is our 2nd mark. Finally, we stick these 2 values into our decay equation. And there is the final answer. This, all written out correctly, is the 3rd mark. Don't take any chances with the easy calculations and write it out. You'd be amazed how many students will add 241 and 4 instead of subtracting. Let's have a look at a different type of decay now. Tritium is an isotope of hydrogen. It decays to an isotope of helium via beta decay. Write the decay equation for this process. So, this is beta decay. Let's recall the atomic and mass numbers of a beta particle, which are -1 and 0 respectively. Again, we'll write out the decay equation, leaving gaps for the helium isotope's atomic and mass numbers. As with the first example, we'll equate the mass numbers, showing that the helium isotope has a mass of 3. And that's mark 1. The same tactic for atomic number shows that the atomic number of helium is 2. You should always take extra care with the beta particle's minus sign. That's our 2nd mark. Finally, we put all of that into the decay equation, which leaves our answer. And that's our 3rd mark. In this video, we covered the different mass and atomic numbers associated with alpha, beta, and gamma radiation. We explained that charge and nucleon number are conserved in a decay, and that, as a consequence of this, total mass and atomic numbers before and after the decay must be equal. Don't forget to check out all our other fantastic revision resources at Save My Exams.